Okay, good afternoon. So let us start the lesson. So in principle, I should start talking about derivatives first. So as I told you that the notion of derivative, I will not cover everything there. The ones that you are supposed to learn is the repetition of what you have learned in calculus, except one more theorem that I will show you. So I was thinking that might be, if there is something left for you to study on your own, it is better to study derivative, but I will try to cover everything, okay, before the lesson ends. So this is why I start today this more important topic that might probably need more explanations. And then, at least for this lesson, we don't use the notion of derivative at all. But even if you want to use it, that's at the level of calculus, so that hopefully you already know about. Yes, I need to read my notes once more so that I can upload it. So it is not uploaded yet, but the classroom notes is uploaded. So if you want, you can have it. Okay. So the first thing we want to talk about is the notion of a Riemann integral. So the first thing we need to know is the notion of a partition. Okay. So have you seen this before, that if you want to calculate the area below a curve, so you in principle you partition it to rectangles and then add up. So I will try to skip those parts. So let me just talk to you about more abstract theory today. So the first thing we want to talk about is the notion of a partition of an interval. So yeah, let me try to explain it on the board. Might be that is easier. So if you have a closed interval from A to B, okay, and I'm always assuming that this is non-degenerate, it means that A is strictly less than B. We talk about partition of this interval. So when I talk about partition of this interval, so it is common we use the notion, the symbol for a set, but I don't know, it's very, very common, even though that's not completely correct, because in the set we do not have the order, but for partition we need the order. Anyway, so when I say that I have a partition of my interval, it means that I have a bunch of points, x0, x1, x2, up to x, I don't know, the last one, let me call it n, so the previous one is x n minus 1, and the last one is xn. Okay, and this is the term. This is the convention we use. X naught is always the first one, and x sub n is always the last one. And as I told you, you have to also respect the order. So I have seen some books, they put pair of brackets around that, rather curly brackets. That might be even better. But anyway, you have to make sure that you are respecting the strictly increasing order. So a partition is just a bunch of numbers in increasing order, starting from A, ending with B. Okay? And each one of these numbers that I choose in my interval, it's called a node. Okay, so for example, if I want to give, this is the real line, here let us say this is A, and here it is B. Okay, so for example, let me choose this point here, and then suddenly I decide to choose this point, and then suddenly I choose that point. That's it, for example. Then what do I say? This is x0, this is x1, this is x2, this is x3, and in this case, this is just x4. So these numbers form my partition here. That's one partition. Of course, it is very clear that I have infinitely many partitions for every interval. Yes, that's my choice. You don't have any rules, so you don't need to. You are not forced to choose them in a regular way. Okay, you can choose them any way that you like. That's called a partition. Okay, one thing that is important is that these intervals are now called subintervals. Okay, and one thing that is important for you to know, that this endpoint belongs to the first subinterval as well as to the second subinterval. So when I say the first subinterval, I mean this closed interval. This is the first subinterval. When I talk about the second subinterval, it means it starts with x1 again, it is closed, and then I go to x2. And then the third one is what? This is the first one, this is the second one. The third one goes from x2 to x3. And then finally the last one starts from x3, including x3, and goes to x4. Okay? So these are called subintervals. So be careful in the Riemann integral theory, when we talk about subintervals, each one of the intermediary points belong to two subintervals, to the left one and to the right one. So if I ask you what is the kth in general for this partition, what is the kth subinterval, what do you say? So this is the first, from 0 to 1. This is the second, from 1 to 2. This is the third, from 2 to 3. So the kth one is this subinterval. Yes? So when I say the kth, remember the index of the left one is 1 unit less, and the index of the right one is exactly this k. And there is another notation for, I would say, delta x sub k. What do I mean by this? I mean the length of exactly the kth interval. Okay, so in this case, this is nothing except x sub k minus x sub k minus 1. So when I say delta x sub k, I have seen some books, they put the k below delta. It doesn't matter which one I have used. No, I have put n here, okay? So delta x sub k means the length of the interval number k, which is the final point minus the initial point. Yes, is that clear? Okay, what more we need to know? Okay, the notion of the norm or mesh of a partition. It means the longest length of these subintervals. So for example, it's not a very good picture, but hopefully you agree this length is the mesh of this partition, because that is the longest one. So, and that is denoted by the norm or the mesh of my partition, the longest. And of course, if I chop them into equal pieces, the mesh is the length of each one of them, because they will be equal. And one thing is very clear. So what do you think will happen if I add these? So I'm only talking about this partition now. So if I start adding them from the first interval to the last interval. By the way, if this ends with n, this is the combination. The notation in different books are different. So remember, when I start with x naught and end at xn, how many intervals I have? I have n plus 1 nodes, number 1, number 2, number 3, number n plus 1, but still I have n number of partitions, okay? So if I ask you, I add them, what does it mean? It means that I am adding the length of each one of these subintervals, and I want to add them up. What will happen? What will happen? So the length of this one plus the length of this one plus the length of this one plus the length of this one. It becomes the total length of my subinterval. So this becomes just simply b minus a. Is that right? Okay. So these are the terminologies that you need to know when it comes to a partition. Let us see what remarks we have. Okay, I think I talked about that remark. So let us not waste the time forward. Okay, this is also a very simple example. So if you don't mind, let us just read it here. So you see that the following sets, one of them p sub 1, the other one p sub 2. The first one is 1, 2, 3, 4, 5, 6. The next one is 1, 1.5, 3, 4.1, 5, 5.75, and 6. Yes? Okay. So do you agree that both of them are partitions of the closed interval from 1 to 6? Yes, all of them start with 1. Both of them start with 1, ends at 6. And then I have a bunch of numbers in the middle, and I have respected the strictly increasing order. So yes, those are partitions. For example, for the first one, these are the subintervals. Do you agree? 1 to 2, 2 to 3, 3 to 4. And if I ask you what is the mesh or what is the norm of this, because the length of all of them is equal to 1, so the highest value is also, highest length is also 1, so the norm of this partition is 1. But for example, when you look at the second partition, so what do you see? I have 7 nodes and therefore I have 6 subintervals. These subintervals have varying lengths. So for example, delta x1 means the length of the first subinterval. The first subinterval is from 1 to 1.5, so delta x1 is the difference between them, which is 0.5. For example, delta x sub 3 means the length of the third interval. So what is the third interval? It goes from where to where? 3 to 4.1. So if I subtract them, the length is 1.1. And if you are patient and do these calculations, I have written all the lengths, and then I see that among these numbers, the biggest one is 1.5. So this means the mesh of this partition is 1.5. So these are extremely simple concepts. Any questions? Okay, so but let us give a non-example. So for example, why the first one is not a partition of the interval from 1 to 6, 1 to 4, 5? Because it ends at 5. It's supposed to end at 6. Why the other one is not like this in the way that it is written, 1, 3, 2, 6? Because this is, you understand this is a little bit sloppy notation, because in the sets there is no difference between them. But anyway, if you see that it is arranged in that way, we don't consider it a partition. If I want to make it a partition, I have to respect the order and write it in the form of 1, 2, 6, 1, 2, 3, and 6. Okay, so this is already, I have talked about this. So remember, when I add them up, this is important. When you add them up, it becomes b minus a. So that's also very simple. One thing might be it is good to talk about regular partition, because I want to talk about this more or less. I want to use it. So what is a regular partition? A regular partition is that you chop your interval into equal pieces. For example, if this P is supposed to be a regular partition, so what do I mean by regular partition? So let us say that this is my partition, x0, x1, up to xn. Okay? It means that delta x1 is equal to delta x2 is equal to the delta xn. This is the meaning of a regular partition. Okay, if the lengths are supposed to be the same, so what is the length of each one of them? The partition of, so I'm talking about this interval always, okay? So it means the total length, which is b minus a, I divide it into n equal pieces, yes? And that is also good to know. For example, what is x0? X0 is just a, but what is, so in principle, when I have a regular partition, I will not call it delta x1, delta x2, etc., because all of them are the same, so I simply write it delta x. So when I am just using delta x without any indices, it means that I am working with a regular partition. So in that regular partition, if I ask you what is x0, of course in any partition x0 is a, but if I ask you what is x1, x1 is a plus delta x. Do you agree? Because I have a, I have 1 delta x. But if I ask you what is x2, x2 is a but plus 2 delta x. And if I continue this list, if I ask you what is a sub k becomes a plus k times delta x. And instead of delta x, I can write this formula. So this becomes k times b minus a over. So if I have a regular partition, I can have a formula for every node. But if I don't have, I am not working with a regular partition, there is no generic formula for the nodes. It depends where you choose them. So you already see that if we can somehow work with these regular partitions, the theory becomes a little bit simpler. Okay, so it will be a little bit cumbersome, but we will come finally by a theorem that we will somehow work with regular partitions at the end. Okay, so these are just terminologies, and that is probably already, this is the word that we use, a refinement of a partition. So if I have two partitions of the same interval, so let us say P and let us say that Q are partitions for this interval. Okay? If P is a subset of Q, then I call Q a refinement of P. It has more points in it. It's a good name because when you have more points, then this structure becomes finer. Yes, the intervals are shorter in principle. But it is, of course, not, it doesn't mean that every interval is shorter from that interval. But in principle, that's a good thing. So that's just the terminology. If this one is a subset of this one, we say this is finer, this is coarser. Yes. Okay, so this is a refinement of this one, if it has more points in it. Okay, that's the terminology. So I have given you one simple example here. So 1, 2, 4, 6 is a partition of this interval. 1, 2, 3, 4, 5, 6 is also a partition of the same interval. So be careful. Refinement is something you define for the same interval. And we also know that P is a subset of Q. So we can say that Q is a refinement of P. Very, very simple ideas. So here, which one is a refinement of the other one in this example? None of them. Because P is not a subset of Q because of existence of 3, and Q is not a subset of P because of the existence of 2, for example. So none of them is a refinement of the other. Okay, and this is probably the last terminology we need, common refinement. So it is a refinement, but it is a common refinement. What does it mean? It means that if you are working with this interval and then you have two partitions, one of them P, the other one Q. If you union them, okay, so this is called a common refinement because it is very clear that when you union them, it is very clear that this one is a subset of this one, and also this one is a subset of that one. Okay, so both of them are true. So this is called of course, when you union them, the order doesn't matter again, but you have to arrange it in the correct order, and then you will have a partition that is called, this is why in some books they use this symbol. So because that's not exactly union. When you union, you don't need to respect the order. Yes, please.
But is it still a regular partition or not?
Pardon? No.
If they're both regular and we do that, it's not going to be regular.
No.
The resulting one, no?
No.
Like we can't guarantee it.
No, it is not guaranteed that the union is still regular. You are right. Yes, you are right. Yes. Because, for example, you can have a partition into two regular partitions. So, for example, and then, so how can I add? So, if the other one is also regular, is the union a regular one?
No, add 1/3 and 2/3 of the distance.
Yes, exactly. So this is 1. So this is 1/2. Let me call it 0 and 1. This is a regular partition for 0 and 1. And as you said, 1/3 here and 2/3 here. Again, this one and this one and this one and that one are regular, but when you put them on top, it is no longer regular. Yes, because this distance is different from that distance. Okay, but these ideas are correct for any generic partitions. Okay, thank you for the question. Okay, so I have given you an example here. I think we can just immediately skip this one. If I give you two partitions, you union them and arrange them in a strictly increasing order, then you have the common partition. Okay? So why did I give you two examples here? I don't know. Yeah, that's just nothing.
This should be in the exam.
Yes. Yes. Okay. Oh, either way, I will talk about the exam again. So exam is simple, so don't worry about it.
Everything's simple.
Yeah.
If you can.
Okay, we don't have to study.
Okay. So now this is the real thing we want to start with, the definition of lower and upper sums. So I want you to understand this definition very well. So let f be a bounded real valued function. So let me give you a little bit of motivation. So the idea is, so if you remember from your calculus course, if you have this and you were supposed to find the area below this function, let me call this function y equals to f of x, and this one is a and this one is b. So do you remember the idea was to chop this interval, for example, in calculus into equal pieces, regular partitions you were working. So let me also be this, let me make it a little bit shorter. Yeah, something like that's good. Something like that. Okay, and then what we do, we start, for example, on this interval, I consider a rectangle that can be inscribed. So let me just chop this interval into pieces like this. And then on this interval, I consider the minimum level of my function and I construct a rectangle there. Okay? Then in the next interval, I consider the minimum of my function and I construct a rectangle here. And then in the next interval, I consider this minimum. And in the next interval, I think the minimum is here again. And then you see that if I start adding the areas of this rectangle, of course it is lower than the area below the curve, but it's a rough approximation to the area of the curve. One thing that matters is something intuitively, and that was by the way the idea behind all these abstractness. So if I chop it into more pieces, what happens? For example, if I put a midpoint, so let me change my color. So if I put a midpoint, so I am increasing, I am refining my interval now, my partition now. And then this time I will concentrate on these points as well. So I have already those points and I'm adding new points. Okay, so here if I want to find the minimum here, the minimum is this one and that one. Here apparently nothing changes. Okay, but here I have one minimum here, which is this one, but another minimum here. So this means this rectangle coincidentally didn't change. The sum of these two rectangles is the same because apparently this was exactly the midpoint. But this one, you see that this rectangle is now, there are two rectangles. And when I add them, the error that I am making is a smaller. Yes, because before that, how much was the error before chopping it into finer pieces? That was the error that I was making in this part. But now when I do it with more number of points, the error that I am making now is this little here plus that little. So it means that I am not making that mistake here. So it is very clear that when I start chopping them up, what happens? The sum of these areas of these rectangles are increasing, but they cannot go beyond the area of the curve, below the curve. And you can do something similar with maximum value. And then, for example, I don't want to mess up the picture. For example, here, if I draw this one, a maximum point, so here, this will give me this rectangle for the maximum. Okay, and then if I do it here, this will give me that one. That's also a maximum. But if I go here, this will be my rectangle, and then this will be my rectangle. So this time you see that I have some extra, I am making some overestimation, yes? So that is the error that I am making. But what is your intuition? If I start chopping it into more pieces, this time the sum of these circumscribed circles, the rectangles, the rectangles that containing this area are getting smaller, but the sum of the areas of these inscribed rectangles are increasing. And if this function is well behaved, we expect that the overestimation gets smaller and smaller, and they get closer to the real area. On the other hand, the ones that we have inscribed rectangles, the area will increase, and they become closer to the area of the rectangle. So that's the idea, okay? So the sum of these rectangles, the areas of these rectangles, is called the lower sum. The sum of the external rectangles is called the upper sum, geometrically. But you don't need any pictures because that's an abstract theory. In principle, you shouldn't need even one single diagram. Okay, so let us now talk about this. But one thing which is important, in this picture, I have drawn, which you learned in calculus, a continuous function. But I don't want to limit myself only to talk about integrals of continuous functions. I want to relax this condition. I don't want to tie my hand with the strong condition of continuity. So I want to make the same ideas working even if my function is not continuous. But I should have some constraint, because if my function is not continuous and it is also not bounded, then I will not be able to construct, for example, the upper rectangles. Okay, so I should have some constraint. So this is why I have written it in red in my notes, that from now on I will talk about a function f which is real valued, and that's good. We are not working in any metric space anymore. We are coming onto the Earth. Yes, we are living on planet Earth. So this means that I have only working with real valued functions on the closed interval from a and b, but bounded. If it is continuous, that is an extra plus for me. But I don't push my function to be continuous. It could be really discontinuous, and this integral theory will be still standing. Okay, so let us now try to understand that. Okay, so what is the, so I give you a function. So let me just now number them properly. So this is 11, 14. So the theory mainly starts from here now. So 11, 14. So let us say that I have a non-degenerate open closed interval, and then I have a function which is defined from a to b to r, but the only constraint I put here is bounded. Bounded means what? Like sine function. So the range is a bounded set in R. And then what I have, I choose a partition for f. So P, so let me write it x0, x1, up to xn. A partition, yes, any partition, not regular. Okay, now when I give you all these things, then I can ask you what is the lower sum of f with respect to that partition. So lower sum is a real number that has two inputs, and it gives you a real number. You have to give what function it is. You have to give on which partition you are working. Okay, so this is defined to be this sum, sigma m sub k delta xk, k goes from 1 to n. Okay, in calculus, m sub k is the minimum of your function on the kth interval. Yes? So if I want to give a picture for you here, so might be this is a good idea. So let me exaggerate this a little bit. So we don't know the dots are here. So this is xa, and let me put some dots here. This is b. Okay, so let us concentrate that this one is the kth interval. X sub k minus 1, x sub k. And then I don't know, for example, you have this. You have a function like this, so you don't know what is happening before that. So and you don't know what is, for example, happening after that. Okay, but you have this within this interval. So let me just put them solid lines because these points are included in the kth interval. Okay, so in calculus, what is m sub k? M sub k is the minimum height of your function on the kth interval. So if I ask you to show it on the picture, what do you show? In this picture, this is m sub k. Yes? This is the lowest value of your function within that interval. Okay? And then if you do the same thing, so it means that you find this minimum and you multiply it by the length. Do you see what you construct? You exactly construct this area. Do you agree? The area of the smaller rectangle. And then you do it for the next subinterval. You do it for all subintervals and then add them up. What you get is a number. That number is called the lower sum of the function f corresponding to this particular partition that you have chosen. Is that right? This was what you learned in calculus. Because in calculus, you mainly work with continuous functions. Continuous functions on closed intervals are guaranteed to have minimum and maximum. But we relax that condition. Of course, again, I drew a continuous one for you. But in principle, this function might not be even continuous. So it means that might be m sub k, if you want to define it as minimum, does not exist. So this is why instead of minimum, I use infimum, which is always guaranteed to exist. Why? Because my function is bounded. So it is also bounded on each subinterval. And if I have a bounded function, it means its range is bounded in R, so it has a supremum and it has a minimum. Okay, so that's the only thing that you should learn. So instead of saying that mk is the minimum, if it is continuous, there is no difference between minimum and infimum. But if it is not continuous, it is not guaranteed to exist. So if little m sub k is the infimum of the values of your function, but x belongs to the kth interval. If you want to understand more or less what is the meaning of this single term, it is this area. Yes? And then similarly, you have upper bound, upper sum. Upper sum is sigma, k goes from 1 to n, capital M sub k, delta xk. So this is exactly similar, but the difference is that instead of choosing the minimum or infimum in its subspace, you choose, in subinterval, you choose the maximum or a supremum. The correct one is the supremum one, of course. So if I ask you to show this, so if I want to understand the meaning of this single term, I go to the kth one, so I find the maximum. In my picture is maximum. So this is mk. And then if I complete this rectangle, the area of this rectangle, the yellow one, is this term. Is that clear? Questions? So the only difference from calculus is that usually, most of the time you are working with continuous functions. If you are working with continuous functions, you can write minimum and maximum. But if you're not working with a continuous function, might be minimum and maximum does not exist. So you need to work with infimum and supremum, which is guaranteed to exist. Why? Again, this is important. Why? Why these numbers are guaranteed to exist? Bounded, yes. Because of this word. When you say that this function is bounded, it means the total range cannot go higher than a level and it cannot go below a level. So this is not the total range, I agree, but if the function in its totality cannot go higher from some point, of course, each piece of it cannot go higher at some point. So they are guaranteed to exist. So this means that it is always possible to talk about lower sum and upper sum. Okay? Anyway, let us immediately start with so let me start with an example and then I come back to this remark. Okay, might be example is better immediately. So I just want you to see that how simple it is, and I will come back to the remark or we derive it together. Okay, so let me write it down here. So this is example 1116. 11, is it 16? Yes. So f of x is this function, very simple function, x squared, and then I have given you a partition of this interval. So the interval that I am working is this closed interval, and I have given you one particular partition, which is 1, 2, 4, 5, 8. Is it regular or not? 1, 2, 4, 5, 8. Apparently it is not regular. Okay? And now what I want to calculate, I want to calculate the lower sum of my function corresponding to this partition. I want to calculate this. Okay, so let us draw some picture here, so that's not bad. So here I have one. Okay, so let me just draw a little bit better. So I have to exaggerate a little bit. So let us say that this point is 1, and this point is 8. And then, if you don't mind, let me draw y equals to x squared. I don't care about the left side. And then let me just draw it like this. It's a little bit exaggerated to make it simpler to write down. Okay. And then we are considering it from here to here. Okay, so this point will be how much? Will be 1. This height will be how much? 64, yes? Because my function is f of x equals to x squared. And let me put the points. The next one is number 2. So here is 2, and then I have 4. This is 1. We can just write it like this. So it's not to scale, okay? But you understand what I mean. So this is my partition. Okay, so how many sub-intervals I have? 1, 2, 3, 4. So I would write it as little m1 delta x1 plus little m2 delta x2 plus little m3 delta x3, and finally m4 1, 2, 3, 4, yes, delta x4. Okay, so let us fill up these numbers. So delta x1 is what? Is the length of the first sub-interval. The length of the first sub-interval is 2 minus 1. I intentionally write it like this. What is m1? Can you help me to find? So where is the first interval? I want you to know. This is your first interval. This is your first interval. On this first, and I am working with a continuous function, so there is no difference between infimum and minimum. What is the lowest height of my function when I am working on this subinterval? Do you agree the lowest point is 1? So this means that m1 is just 1 to power 2. Why to power 2? Because in principle I have to put 1 into my function and get this 1. 1 to power 2 is 1. But I intentionally write it here so that when you want to read it yourself, you understand it. So okay, help me to do the other one. First tell me what is delta x2. Delta x2 is the length of the second subinterval. This was the first subinterval. This is the second subinterval. So this becomes 4 minus 2. And what should I do? What is the lowest value here? What is the lowest value of my function when I am working on this interval? The lowest value is this one. What is the height? Is 2 to power 2. Because this is 2, I have to feed it into my function. So it is 2 to power 2. And then I don't think it needs explanation. So let us do that. So for the next one, the length is 5 minus 4. And then I have to write 4 to power 2. And then the next one is 8 minus 5. And then I have to write 5 to power 2. Yes? And then, of course, what you get is a number. Yes? So this becomes 1. This becomes 8. This becomes 16. This becomes 75. 91, 100. So this number is what you get for LFP. Yes? Okay, and you can do something similar for UFP. So the only difference is that you have capital the M1 up to, so let me write 2 terms. I don't want to complete it because this is very simple. Okay, so can you write the first one? What is the first one? You are working in the first interval, but this time you are working with maximum because there is no difference. So what is maximum now? In the first interval, what is my maximum?
2.
Is 2 to power 2. Yes, because 2 is the maximizer, but I want the maximum. The height is matters for me. So 2, so in this first interval, maximum occurs as 2, but the height of the maximum is 2 to power 2, and then I would write it 2 minus 1. So what is the next one? What's the next one?
4.
What? 4 to power 2, and then I would write it multiplied by 4 minus 2, and then you can continue this one. So it's very simple. Now, if I want to go back to this remark, this last line, I want you to know about that. But let us derive it together, okay? So this one is something important because you know that no matter which partition I choose, the lower partition, the lower sum is always less than or equal to the upper sum. And there is also a threshold for the upper sums, and there is a threshold for the lower sums. Okay, so that's good to know about that. So if we have this example now 15, so when you have a function from a to b which is bounded, what does it mean, by the way? So it is just in R. So when I say bounded, it means that there exist two numbers, for example little m or capital M in R, such that for every x in a and b, m is less than or equal to f of x is less than or equal to capital M. That is the meaning of being bounded. When you say a function is bounded, it means this. It means that the values of f cannot go beyond some value, cannot go below some value. Okay, that's the meaning of that. Okay, but now do you agree that for every k, and then let us say that this is your partition. Partition is x naught up to xn, a partition for AB. So do you agree that for every k in 1 up to n, what do you have? You have little mk is less than or equal to capital MK. Do you agree with this one? It is because mk is the infimum, capital MK is the supremum of the same set of values, of the same set. So the infimum is always less than. But now, this one, I hope that you agree, it is less than m. Because m is the upper bound for the totality of the function. So it is clearly greater than m sub k as well. Because that is the highest value of my function within one subinterval. This is the highest value of my function in totality. So it's very clear that this happens. And then, of course, this is also greater than or m. Do you agree? Okay, now, if what we do, we multiply everything by delta xk. So then what happens, this becomes m delta xk is less than or equal to mk delta xk. By the way, delta xk is positive, so I don't need to be worried about the direction. And that is less than or equal to m delta xk. And what we do, we sum them up. Okay, so what I will do, so let me just be lazy and put a sum here. After multiplying, I sum them up, and I sum this up, and I will sum this up as well, and sum this up. Okay, so if I ask you what is this one, this is nothing except LFP. If I ask you what is this one, this is nothing except UFP. So this one remains smaller. Okay, but this one, what happens for this one? M is a fixed number. I can pull it out from the sigma. So sigma will act on this one, but this becomes B minus A. So it is very clear that this becomes M times B minus A, less than or equal to that. And finally, the same story here, capital M B minus A. So it's a very nice relation to know. So if you have the lower sum and you have an upper sum with the same partition, it is clearly the lower sum is less than or equal to the upper sum. But upper sum, all of them have an upper bound, and lower sums have a lower bound. Okay. So now let us go to the next theorem. It's a simple but important theorem. So we want to understand, you already can answer it, yes? So what was your intuition here? If I start refining my partition, what do you think will happen to the lower sums? What do you think will happen to the upper sums? We had this intuition here, yes?
They will approach each other.
They will approach each other, but in which way? The lower sums will grow,
Yes.
and the upper sums will shrink. Okay, so that is important to know. So that is the topic of this theory. So I want you to prove this one because I want you to see what way we sometimes prove these ideas. Okay, so this is theorem 1117. So what we have the bounded function as always, so I don't write it all the time to save time. But here we have two partitions. So I have an interval, I have two partitions of A and B. So let me write partition of A and B. Yes. And then one of them is a refinement of the other one. So P, for example, is subset of Q. We want to show that if you calculate the lower sum of your function, so let me write everything. So if you calculate the lower sum of your function with respect to P, and you write the lower sum of the same function, but this time with respect to this new partition Q. Q is the refinement. We learned that intuitively that they should grow. So this means that this is less than or equal to this. We want to prove this. This is not that obvious, by the way. Okay? And then we want to show that the other way around. Is my notation consistent with what I have written there? Yes. If Q is a refinement of P, means this. That's correct. So if we want to prove that, our intuition really is correct here. So let us go at least to a SketchUp proof or proof here. So do you have an idea how to prove it? Because in principle, when you say that Q is a refinement of P, this will definitely contain the points of P, but it might have a lot of more points. But we don't want to make trouble for ourselves. I want you to understand that if I can prove this happens, in the case that Q has one extra point, do you agree we are more or less done? If this refinement has only one extra point, and I can convince you that this is correct, this means somehow I will be done. I need to write one sentence and I will be done. First of all, do you agree with this one? If yes, why? Yes?
Because if it works with one, then we can take another partition with one
more point. So we can add one, yes? So it means that if I can prove that this works for 1 point extra, then I will go to the other one with 2. So the other one with 2 point extra with respect to the next one has 1 extra point. So I can just go up. Okay? So it is enough to prove it for just one single point. But of course I have written. So this is a sketch of a proof, okay? Because I don't want to write all those details. Okay, but so let us try to understand that. Okay, so let us, for example, let us say that P is this one, x0, x1, up to xi minus xk minus 2, xk minus 1, xk plus 1. I intentionally write these things so that you understand. And then xk plus 2 up to xn finally. You know that x0 is A, you know xn is B. So this is my partition. Okay, so now let us assume that Q is the same, but with one extra point within the kth interval. Okay, so let us say that Q is x1, x0, x1 up to xk minus 2, and then xk minus 1. But now my extra point, if you don't mind, let me call it C, and then I have the rest of it. Okay, so I have these two partitions. So the cube is a refinement of P, but has only one extra point in the kth interval. Yes? Okay, and now let us, for example, calculate this one. And I want your help, okay? So if I want to write the correct formula for this one, LF with Q, what do you write? You write M naught, you write M1 delta X1, which is X1 minus X0, yes? And then you write M2 X2 minus X1. And then you continue, for example, here, this is M, which number is that? If this is 2, it starts here. So it becomes Fk minus 2, K minus 1, xk minus 1 minus xk minus 2. Do you agree? And now, can you help me? What should I write now? So this is the infimum on the first subinterval. This is the infimum on the second subinterval. And I continue here. Up to here, I have written down. So I want to go to the next one. So I would write what?
MK.
Let me don't write MK because I want to distinguish it from that one. If you don't mind, let me call it M star. M star is the infimum here. Okay, but I have to write C minus xk minus 1. Okay, and then I will have another one. So if you don't mind, let me call it M double star or any number, anything that you like. And then I would write xk minus C. Yes, we have done up to here. So let us go one more step. So what should I write? I would write it because I am using these indices for this partition. Okay, so then I would write it as M. When I go to the next one, xk plus 1 minus xk, and this I would call it mk plus 1. Yes, and then the next one will be mk plus 2, and then I will have xk plus 2 minus xk plus 1. And then finally, I will go to the last one, mn. Yeah, I'm just making it, I don't know, might be I'm making it a little bit hard for you. But I hope that you understand me. So I am using these symbols, M's, these stars are the new ones. But these, the ones without a star are also appearing here. Do you agree? Okay, but can you see what is happening? Let me consider these terms, this term, and this term, and this term. I want to write something for all these ones that I have underlined. What can I write? Can I write it as L FP? Can I? The ones underlined. There are two terms. I will add them later. So let me add them in front of you. So I will add them here. So don't worry about those. So my question is that for the ones underlined, can I write this or I have to fine tune it?
You should add MK times.
Add or subtract? I have to subtract. Yes, because LFK also consists the MK third.
Yeah.
It is missing here. So if I write LFP, I am actually making some extra things to it. So I would subtract it. But what should I subtract? Can you tell me?
MK.
MK with
XK.
minus XK minus. Do you agree? Because when I ask you to write for this one, you have to write x1 minus x0 multiplied by a1. You have to write this one minus that one multiplied by ak minus 1. But you also have to write xk minus 1 multiplied by m sub k, which is missing. So when I write this one, that is not correct unless I take that off. So now what I am claiming is that this expression in total is the sum of these terms underlined. Is that right? Okay, but now this one becomes greater than or equal to, I will copy and paste this one. I will copy and paste this one. Okay, but what can I write? I will write something, then I will ask your opinion. Do you buy it or you think I am lying? So you see, I didn't touch this part, copy and paste. So what I did is, instead of m star, I put m sub k. And instead of m double star, I put also m sub k. And I just copied and pasted this one. So in principle, what I am claiming is this one. If you agree with this one, we are done. Do you agree that m star is greater than or equal to mk? Yes? Because what is m star? M star is the minimum of this sub-interval. So this interval has now been broken to two sub-intervals. Where is C? Sorry, these two sub-intervals. So this one of them is this one, the other one is this one. Yes? From xk sub minus 1 to xk, which was one sub-interval, now I have two sub-intervals. So m star is the minimum on this one, and m double star is the minimum or infimum of this one. But what is m sub k? M sub k is the infimum of on the total interval. So do you agree that now m star should be greater than or equal to mk? Because m star is the infimum. Let us talk about minimum. Minimum is easier for you. So m star is the minimum on sub-interval, but this one is the minimum of on the total interval. So it is clear that this one should be greater than or equal to that. Is that right? So this one is greater than this one. So this one was valid. For the same reason, m double star is also greater than that. For the same reason. And then you see, you can immediately calculate this. What is this one? Greater than or equal. Now again, I go to equality. I copy and paste this one. Between all these terms, I factor mk out. This is a minus sign, so it becomes minus xk plus xk minus 1. This one is c minus xk minus 1. This one is xk minus c. I copy and paste this one, and I think we are done, are we? Because now minus x sub k, cancel that one, plus c, cancel that one, and this one, cancel that. That's equal. So this means that I started for LFQ, it was equal up to here. This one is greater than or equal to this one, and again, this one is equal to that one. So this means this number is greater than or equal to that number. Is that clear? That's a sketch of proof. This is not complete, because then you should explain, if you want to have the proof, what happens if I have more than 1 point, but that is the explanation you take. Okay, any questions? Okay, so we can have a break, then we come back.